everyone. Today we're going to talk to you about optimizing your mobile applications on Unity. But first, we just want to introduce ourselves so you know who we are. My name is Mark. I'm a developer relations engineer at Unity. I've been at Unity for almost 6 years now. Currently, I'm based in North America, where I visit our customers on site and help them optimize their games, fix bugs, and unblock them from shipping their game. On top of that, I'm using the information I'm gathering from these visits to currently prepare a set of best practice library documents that we hope to ship on our website soon.
Hello, my name is Ian. I am also an enterprise support relations engineer with Unity. And essentially, the difference between myself and Mark is that whereas Mark handles our customers in North America, I am based in Europe. But I do the exact same job, I write the same guides, and I conduct the same project reviews.
Okay, so what we want to talk to you today about optimizing your mobile applications is getting good data is the key to optimizing your application. And we want to show you how to do this. We will also discuss some general best practices, along with the common problems and the solutions to those problems.
And we're going to divide this talk into two sections. Well, first, three sections. We're going to start with profiling, with getting data. Then we'll move into talking about measuring and reducing the memory consumption of your game. And finally, we'll wrap up by discussing CPU performance. So, to discuss optimization, we first have to start by talking about profiling, because any attempt at optimizing any application must start with good data. If you go in blind, you are going to end up doing a lot of work for potentially not a lot of benefit. So to get good data, what you really need is good tools. We've listed some on this slide: Instruments, vTune, the Snapdragon Profiler, Unity Editor. We also recommend Intel GPA. These provide the best starting point for most developers. Unity's built-in profiler is best for looking at how an application handles memory. It has a lot of other tools in there, but among all of the ones here on this slide, it's best at profiling memory, especially if you're using Unity 5.3. A little later on, Mark is going to discuss the new memory profiling APIs and tools that we've added. The Unity profiler, however, is limited. It's not easy to search for specific problems, and it's not easy to get data at certain points of an application's life cycle. However, since we are talking about mobile applications, we're fortunate. We can use native tools. Now, the best tool available right now is Instruments. This is a free tool. It is included with Xcode. And the best thing about it is that it can capture extremely detailed and extremely precise information. You can get millisecond timings for every single method that is ever called in your application. It's the best tool that is available for profiling the scripts that you've written. If you are not familiar with how to run Instruments, it is for iOS and OS X only, unfortunately. However, we did post a blog at this URL that goes over the basics. We will also post these slides after the talk, so you don't need to take a photo of everything. Anyway, let me show you a screenshot from Instruments. When you run it, you'll run the time profiler, where this is from, and you'll see this sort of call tree. You can see here that it lists all of the methods that are running inside of your game. Now, this is not just your scripts. This is Unity's internal C++ code as well. So if you have some time and you can crawl around inside of here, you can learn a lot about how Unity works. Now, on this slide, I've highlighted a part of the call tree that's inside the Start Unity method. This method runs while the splash screen is visible. During this time, Unity is initializing its internal systems, but there's also two places where your project and your project's settings can affect the execution time. So here you'll see the function player load global managers. Inside there, if we opened it up, you would find a call to an object called the resource manager. The resource manager object loads an index of the files within your resources folder. I will discuss this in more detail later. Second, there's a function that says Unity load application. It's at the bottom of the highlight. This function loads and initializes the first scene in your game. So it is loading all the textures and models you need to run the first scene, but it also loads all the mono-behavior scripts. Not only does it load them, it actually runs all the awake callbacks that you have in your mono-behaviors. So if you have a long-running deserialization in an awake callback, that can actually cause your application to spend much more time on the splash screen. Instruments also provides excellent data when your game is running. Now, Instruments provides aggregate data. Unlike the Unity profiler, you can select and view data that comes from multiple frames. So you can take a 10-second slice of your run and compare the performance of your different systems. Here, I've highlighted the player loop function. This is actually Unity's main loop. The code inside of it runs once per frame. Now, a lot of things happen inside the main loop, as you might imagine, but I'm going to talk about the 6 most interesting ones in some detail. First, and the most interesting thing, is the base behavior manager object. This will call 3 templated functions. The behavior manager template will call all of your update loops. The late behavior manager template will call your late update loops. And the fixed behavior manager will call your fixed update loops. So when you want to examine the performance of the scripts you have written, this is where you start. Second, there will be a call to the physics manager. It will be the fixed update function. This call contains the actual cost of running physX in your scene. It applies forces, it moves colliders, and so on. If you have any physics callbacks, like on collision enter, on trigger stay, on collision stay, these will also be here. Third, delayed call manager. This object runs coroutines. Now, coroutines are complicated. I will discuss them more very shortly. Fourth, player render. This is Unity's rendering system. Anything related to graphics runs here. It calls objects, it calculates dynamic batches if you have that turned on, and it submits all the draw calls to your GPU. Any image effects, any rendering-based script callbacks, like on will render object or on pre-call, those will also show up here. Generally, you want this to be the most expensive thing in any slice of runtime. Obviously, you're making a game, you want your players to see the game that they're playing. If you're using Unity's UI system, you may see some computation in the UI canvas manager. Now, Unity's UI system does its batch computation inside this function. So if you have a large Unity UI, you may see the canvas profiler popping up inside your call tree. If you're running pre-computed real-time GI or reflection probes, these will show up under the Enlighten runtime manager. Unlike all the other things I've mentioned, there's no real script that can affect this. If you need to reduce the cost of this, you have to reduce the number of reflection probes in your scene, reduce their sample rate, or you have to reduce the quality or number of things affected by pre-computed real-time GI. Now, there's a lot of subsystems inside of Unity, but let's look at what I first talked about, profiling your scripts. In this screenshot, you can see that the behavior manager, up at the top there, is running the C# scripts. Now, if you follow the call tree down, you'll see that when invoking C# scripts, we go through a scripting invocation object. On this slide, all the mono behaviors in this scene that have update loops are listed beside that red arrow. So what you can see in this profiling run of Unity's standard assets project is that the update method of the event system class is 100 times more expensive than anything else in our scene. So if we were really going to optimize this scene, we'd open that up. and we'd actually see every single thing that is consuming those 1,350 milliseconds. Spoiler alert, it's physics raycasts. Now earlier I did mention that coroutines were a little strange, so let's look at one of those next. Here is the delayed call manager running a coroutine. Again, you see the scripting invocation object, roughly in the middle of the highlight. Then it goes into a method with a strange name. If you look closely and it's readable on the screen, you can see that the coroutine is actually called do bob cycle, right here. This is a coroutine that runs the head bob when the player is walking around through the scene. Now, since this coroutine, this head bob coroutine, runs over many frames, most of the cost of that coroutine will show up here inside the delayed call manager. But not all of it. You see, coroutines are actually supported by an object. This object is generated automatically by the C# compiler. You don't have to do anything to create it. And the object tracks the state of the coroutine. Unity invokes the object whenever it wants the coroutine to run. Because of this, the cost of the coroutine will be split into two places. All the code that runs from the start of the coroutine until the coroutine yields will appear in the call tree wherever the coroutine is started. That is, wherever you call start coroutine. So you may end up seeing some of its cost in the update loop or some other scripting method. However, the rest of the coroutine's cost, from the first time the coroutine resumes until the coroutine ends, that will all show up in the delayed call manager. Now, hopefully your coroutines yield more than once, so in that case, the majority of their CPU time will be spent in the delayed call manager. Now, sometimes when you write a game, there is some core code, string manipulation, some mathematical code that you've written, and this is used all over your game. And sometimes this core code isn't as fast as it could be. To find these cases, use Instruments' search function. There's a little box just in the upper right of the call tree. What you do is you simply type a method or an object name into that search box, and Instruments will show you only the parts of the call tree that include methods or objects with the matching name. Now, there's two major things that most games spend unnecessary time on. That's string manipulation and boxing. We're going to talk about these a lot in a little while.
Okay, so Ian has talked now about setting up the profiler and common things you can look at in terms of CPU usage. I want to now talk more about memory, common causes of excess memory consumption, and very, very simple ways that you can reduce this. So, excuse me. The first thing I want to talk about is the memory profiler tool that was added in Unity 5.3. This allows the users to examine the full contents of memory. Both native and managed allocations will be displayed in this tool. You can use this tool to track down all problematic areas of memory within your Unity title. And the main power of this tool lies in the ability to trace the reference chain back to the variable that is holding onto the object in memory. Further to this, the tool is built on a public API, so you can actually modify the way the tool works for your exact needs. So, this tool, it doesn't actually ship with the Unity editor. It's actually hosted on our Bitbucket website, and you need to download it from there. It's just an editor folder, so you just need to grab that folder and drop it into your project to use it. You then need to connect the profiler as you normally would for a development build on device, and then you can take snapshots of the memory from there. The one drawback to this tool is that it only works on IL to CBP. So currently that's iOS and Android. If you run it on a platform that has the monoscripting backend, you will only see the native memory allocations, and they won't include any reference chains back to the objects holding onto them in memory. So let's look at a couple of use cases. These are very common. I see them a lot in the wild, and they're very easy to fix. So let's start with duplicated textures. So we have two textures on screen here. They're both the same, but unfortunately there's no way for me to show that on one slide. So this is a common issue when dealing with asset bundles, and if you're developing mobile, you're using asset bundles. You unload an asset bundle with the false flag, so that's asset bundle.unload false. Internally, at this point, Unity has no way of knowing that the texture was loaded from an asset bundle. So you can then reload the asset bundle and reload the same asset, and then you have two copies of the same texture in memory. So we can see here, the textures have the same name, the screens may be a little low resolution, but they have different instance IDs. So it's the same image, but you have two copies. Another common example is image effects. Now, consider iPad Air 2. If you have an image effect that uses a render texture that is full native resolution on the device, it actually takes 36 megabytes of memory to do this. And native iPad Air 2 is effectively 4K. Consoles aren't rendering 4K. PC gamers are only just rendering 4K, so downsize your screen resolution. You downsize to 1080p, this becomes a 60 megabyte texture, which saves enough memory for 32 1K compressed textures in your game. So you can really add a lot more content without really compromising the visual quality at that point. So downsizing the resolution of your game is a very quick and easy way to save memory. Now, I want to talk about assets. And this is the #1 cause of memory problems in Unity applications I find in the wild. So what I want to discuss is auditing the assets in your project. And what do I mean by audit your assets? Simply put, it means developing an automated systems for controlling the import settings on the assets in your Unity project. And by controlling these settings, the intention is that your project will have the correct import settings applied to all the assets. So the people on your project are human. They are prone to making mistakes. This is a very tedious task to do manually. And by automating the process, you can hope to eliminate the mistakes that can happen in this. Mistakes cost time, so they should be avoided in any way possible. So, common errors with your assets in your project. Insane texture sizes. If you have a 4K uncompressed texture, and in the past the NGUI extension would generate these by default, it will take 60 megabytes of memory. This is about a third of the memory you have available on low-end mobile devices. Just by compressing that texture, you will save around 52 megabytes of memory. So it's one checkbox, and you've reduced your memory footprint by a massive amount. So that's a very common problem. Asset compression, again, meshes with the correct import settings will be smaller. Audio files as well with the correct import settings will be smaller. But I will discuss that just briefly. But the thing to remember is every asset on every platform needs a different set of import settings for it to be optimal in your project. Okay, so I just want to run through a very quick example of a basic asset post-processor that can be set up to control the import settings on your project. So firstly, you need to set up a class that inherits from asset post-processor. The asset post-processor class receives callbacks. Anytime the import settings are changed on an asset, or anytime you import an asset for the first time. And this is very useful for applying the defaults at this very point. Because we all know the import process on Unity can be a little bit slow at times. The on pre-process methods are the ones you absolutely want to implement, however. So this is on pre-process texture, on pre-process model, on pre-process animation, and on pre-process audio. And these allow you to apply the settings to your assets before Unity has even imported them. So, This example shows how you would use on preprocessed model to override the default read-write setting on models you import. So the asset post-processor class has an asset importer field in it, but we need to cast this to model importer because we're dealing with models. We then check if model importer is readable. So this is the read-write enabled checkbox that you would see on the inspector. If it is true, we change it to false. We then save and re-import the asset. Now at this point, it actually calls this method again, but model importer will not be readable, so it won't actually do anything. And it will just allow your settings to fall through. So, I want to talk now about some other common rules. Like, these are the very simplest things you can do to change to gain quick memory savings on your asset. First off, make sure read-write is disabled. Read-write will store 2 copies of your asset in memory. So just by disabling this, or making sure this is disabled, you will halve the memory footprint of all your textures. Disabling bitmaps wherever possible is another great memory saving. This will save you 1/3 of your memory, and you can disable it on anything where the Z depth of the object will not change in your game. For 3D objects that do have Z depth change, it is worth considering leaving on because you can save some GPU time. Make sure your textures are compressed. So for iOS, PVRTC, and Android, whichever texture compression format is best suited to the GPU you're tackling. And then keep textures as small as you possibly can. The bitmap view in the scene view will help with this. It allows you to see the textile density of the objects on screen. For models, again, make sure read-write is disabled. This is actually on by default in Unity, so that was why I showed the other example. You want to apply that to all models in your game, unless you're manipulating the mesh via script. Mesh compression will also save on disk space, but use it sparingly, as too much compression will affect the data and alter the appearance of your meshes. So it's very much a process where you have to go through your assets and figure out how much compression you can apply to them. For audio, import the raw PCM WAV files in as high a quality as you can. Unity actually compresses the audio files as part of the build process. So if you bring in a pre-compressed audio file, you're actually compressing it twice, and you're going to lose some quality there. So for audio files, there is native support for compressed MP3 on iOS and OGG Vorbis on Android. So use those settings accordingly per platform. And then you can force mono and set more bit rates to save even more kilobytes if you need to. So I want to move on now to the managed heap. This is problematic in a lot of games in Unity. The new memory profiler will help to track down problems now, but there are also very simple things that you can do to prevent it being a problem in the first place. So, managed memory, how it works. The heap contains all objects allocated for assets and script. So the white area here represents the entire managed heap, and the objects inside it are the objects that you would have allocated. So when we need some more memory for managed objects, it will go into a space in the heap. And then periodically, the garbage collector will run. It will look for unused objects. When it finds one, that used object is then deleted. That's your basic garbage collection process. Now, be aware that that gap has been left behind. So there is now a hole in memory, and the memory is fragmented. And Unity's managed heap never collapses. It doesn't contract that space. So it is just there permanently. So when we try to allocate a new object and there isn't enough space, then what we have to do is expand the managed heap. We have to allocate more memory so this object can fit in there. And now the managed heap is permanently increased in size. You can never get back the memory that has been allocated. So the main problems with managed memory in Unity are the heap only ever expands. It can never shrink. And the parts of the managed heap that are unused by managed objects cannot be allocated for native objects. It is effectively wasted memory. Now, let's talk about how you can end up in those situations and ways you can get out of it. So, temporary allocations within your script code are extremely bad for your game. They should be avoided at all costs. And let's take a very simple example. So, your scripts are allocating 1 kilobyte of memory every frame. Over 60 frames, that's 60 kilobytes a second. And over 1 minute, that's 3.6 megabytes. Now, consider this. The garbage collector will only ever run as the managed heap is running out of space, unless you're manually triggering it. So if you're at the point where you've almost run out of space in the managed heap, and then do a larger operation, such as loading, you will be forced to expand the managed heap. All those temporary allocations will be deallocated, and you will be left with huge amounts of unused space in your managed heap. So it's very important to eliminate these managed temporary allocations wherever possible. And to do that, you can just use the regular Unity profiler. If you use the CPU tab, and then sort by GC alloc column. Everything that you can eliminate should show in that column. But be aware that there are certain things that will show in the editor that do not happen on device. So always test on device. So how can we stop these temporary allocations? Very simple things you can do, which people seem to forget, is you can reuse your generic collections, your lists, your dictionaries, your hash sets. So if you call .clear on them, it will remove the content, but it doesn't deallocate the memory, so you can just reuse the collection. So don't keep them in temporary local scope, make them fields and reuse them wherever possible. Avoid any forms of string manipulation whenever possible. Strings are immutable, so every time you change it, you allocate a new one. Use string builders wherever possible to help with this problem. That should help there. And then avoid anonymous methods and closures. They always allocate memory, and use them sparingly, as they can only be treated as reference types, and therefore are always allocated to the managed heap. Boxing is another common cause of temporary managed allocations, and these happen when value types are temporarily allocated as reference types. So an example here, you have a value type int x, and then you have your reference type object, and then when you do the comparison, the dot equals takes an object, so C# generates the int as an object temporarily to do the comparison, and this is causing these temporary allocations. The single most common runtime managed allocation that we see is for each loops. When the loop begins, a temporary enumerator object is allocated, and this is actually specific to Unity's version of Mono, and it happens on our ILTCP as well. This temporary allocation is bad because it's temporary allocation, but you should also be aware that for each loops generate more bytecode instructions, so they're actually slower in CPU usage, and they also have a method invocation which is incredibly slow in C#. So if you can avoid using a for each loop, don't use a for each loop. Always use for where possible. It is even worth reconsidering your data choice and how you're storing an object to avoid for each loops. There are some Unity APIs which cause these temporary allocations. For example, the APIs that return arrays, it always allocates a new copy every time you access it, even if the data isn't changed. So, for example, on mobile devices, there is the input.touches array. So every time round this loop, we're allocating an entirely new copy of the whole array just to access one element. By moving the allocation outside of the loop, we're only doing it once, and then we're accessing the cached copy. It's very, very simple to gain very, very quick benefits just by reorganizing a little part of your code. Now I'm going to hand you back off to Ian, who's going to talk more about CPU.
Okay, thank you, Mark. When we're talking about CPU performance, again, we can break it into two sections. We'll talk first about loading time and then about runtime performance. And of course, you always want your loading time to be as short as possible. You want to get your players playing the game as fast as possible because no one likes looking at a loading screen. Now, one of the major reasons that we find when we're looking at products for slow loading times is parsing text. A lot of people use JSON or XML to hold their game data. Many JSON and XML parsers are actually using reflection under the hood. Now, reflection lets your parser be very flexible, and that's great when you're still developing your game. You can iterate very quickly on your gameplay. However, reflection is very, very slow. Now, if you're on Unity 5.3, you might be able to use Unity's built-in JSON utility class. This class uses Unity's internal serialization system. It's actually quite fast compared to most of the other JSON parsers available in C#. If you're using protobuf, please use the precompiled or code-generated version of protobuf to do your serialization. It's much faster than the reflection-based one. There are, however, 3 strategies you can use to speed up your data loading. For some kinds of data, you can avoid parsing text entirely. If your game loads data that doesn't change very often, you could write a system that bakes that JSON file or that XML file into a format that Unity can serialize natively, like a scriptable object. This is usually useful for things like levels or data that only changes when you build your game. The nice thing about loading binary data is that it completely avoids the problem of parsing text. In fact, when deserializing a scriptable object or a native C# serializable type, Unity will just copy the bytes off of disk directly into memory. It's the fastest possible thing you can do. Now, there are a lot of cases where this isn't possible, where you need data that is generated after your application has been built, where you can't be rebuilding asset bundles with binary objects all the time. In that case, what you could try to do is reduce the amount of work that is done at a single time. For example, if you have a large number of levels in one file, split it out into multiple different level files. Split your data into smaller chunks, and then parse only the data that you need right now. Now, once you've parsed it, parse that data from text to binary, cache the binary result, of course. You don't want to parse text twice. But there are some cases where neither of these two things are possible. You can't split up your data, and you can't convert it to binary. In this case, you could consider moving your game's text parsing and deserialization to a worker thread. You would just use C#'s built-in threading class. Now, this is a dangerous technique. It is very, very easy to create race conditions. Multi-threaded programming is difficult. However, it can be very powerful as long as you're careful with synchronization. Remember, though, you cannot deserialize any Unity data types on a worker thread. You cannot deserialize a scriptable object on a worker thread. Only pure C# types are safe to deserialize on threads other than the main thread. Another common problem, the resources folder. If you have too many files inside of it, then the loading time of your game can become very long. This is because when building your game, Unity serializes all the assets in all of your resources folders into one giant file. it then calculates an index for each asset that is inside of that giant file so that it can load them. That's the index I mentioned at the very start of this talk. Now that index grows as the number of files inside your resources folder grows. So if you have thousands of files in your resources folder, simply loading that index can take hundreds of milliseconds on a slow device. On a really slow Android device, if you have tens of thousands of objects in your resources folder, I have seen it take upwards of 10 seconds just to transfer this index. The only way to fix this problem is to move assets to asset bundles. Let's move on and talk about runtime performance. Obviously, players want your game to run smoothly with a good frame rate. Now, many performance problems are unique to each game. Always, always profile your game using the tools we've mentioned to discover exactly which part of your code is slow. But I will go over a few things that are common across many of the projects we've worked on. One thing that's very easy to speed up, if you are addressing a material or animator property, a lot of people simply use strings, like the color and attack that I've highlighted here in red. Every time we call material set color, or every time we call animator set trigger, Unity will hash that string into an integer ID every single time we call it. Now, hashing a single string is not too expensive, but most games don't do this once per frame. They will do this tens of times per frame, or hundreds of times per frame. And the fix is very simple. You just hash the strings once. You can make a class somewhere that holds the property IDs, and then you use these two methods: shader property to ID for materials and shaders, and animator string to hash for animator properties. These will return an integer, which you simply capture off and use whenever you call set color, set trigger, or any other get or set method on a material, shader, or animator. This, of course, entirely avoids the hashing. It's very simple to do. It's effectively free performance, so I encourage everyone to go out and fix their games right now. Two more common performance problems. We've mentioned them before: string manipulation and boxing. But these don't just waste memory. They're actually quite expensive on the CPU as well. Fortunately, string manipulation is very easy to find. You can just search your source code. However, it can be very hard to fix without big architectural changes. If you do have to manipulate strings, be aware, regular expressions are extremely expensive. Every time you perform any operation on a regular expression, it allocates multiple arrays, internally and temporarily, for every operation. The built-in starts with and ends with APIs on the string class, these are surprisingly slow. They are more than 100 times slower than a hand-coded replacement. Now, you can use the string comparison ordinal to reduce that cost slightly, but it is still not the 2 order of magnitude improvement you will have by replacing them. Boxing, very hard to see in source code, especially even for experienced programmers. C# makes it almost too easy to box value types. Mark showed you a little example earlier. You can see that it was invisible effectively. Fortunately, in instruments, it's easy to find boxing. If you search the profiling tab run for ::box, you'll get something that looks like this. Now you can see here that one of our coroutines is boxing. We've highlighted it there in the middle. In fact, if you look closely, very closely, you will see that there is no method call between the invocation of our coroutine and the boxing. So in fact, this boxing isn't coming from a coroutine at all. This is internal to Unity. You see, whenever Unity invokes a coroutine, that coroutine has to return a Boolean value. The way in Unity's current version of Mono, and in Unity's current version of IL to CPP, that Boolean value is boxed. So every time a coroutine runs, it will box that Boolean value, and that will show up here. Completely unnecessary memory allocation internal to Unity. What can you do about that? Nothing. Mark and I are actually working with our scripting team to fix this. I would like to thank you. Oh, my thank you slide went away. There we are. Thank you. I want to thank everyone here at Unity Korea for hosting us and our translation team, because we have not made their time easy. If anyone has any questions, we would be happy to take them now. There should be a microphone coming around.
We would also like to remind everyone to take the survey on the top,
Yes.
if possible. Thanks.
예, 안녕하세요. 아까 메모리 관련해서 홀이 생긴다고 하셨는데, 제가 알기로 모노나 단넷 같은 경우는 제너레이셔널 가비지 컬렉터를 사용해서 가비지 컬렉터에서 힙에서 매니지드 힙에서 삭제가 된 이후에 컴팩팅 과정을 거쳐서 홀이 생기지 않는 걸로 알고 있거든요. 물론 사이즈가 큰 할당된 거에 대해서는 홀이 생기는 걸로 알고 있는데, 그 부분에 대한 내용이 없어서 그런데, 혹시 IL2CPP라든지 또는 모노에서는 IL2CPP는 이제 C샵이 아니고 CPP니까 그런 부분이 다른 부분이 있는지 궁금합니다.
No, so you are correct. Currently, we are trying to make IL to CPP match Mono's behavior. Now, the compacting process is in newer versions of Mono and is in newer versions of C#. As many of the people in this room are most likely aware, Unity is not on those versions. Unity uses the Bohm garbage collection algorithm. It is non-compacting, and is in fact non-generational as well. Does that answer your question?
Yes, just further to what Ian said, it's on our public roadmap for our .NET runtime upgrade. So once that gets a version, you'll know when we're getting a compacted garbage collector.
한 가지 더 질문이 있는데요. 출처가 명확하진 않은데, 유니티에서는 다른 스레드를 이제 사용하지 않을 것을 권장을 하고 있는 걸로 이렇게 출처는 명확하지 않게 들었는데, 이런 스레드를 유저가 만들어서, 개발자가 만들어 사용을 하게 되면, 예를 들어서 멀티 스레드 렌더링이라든가 이런 거에 있어서 영향을 줘서 렌더링에 부하가 있다든가 좀 문제가 생긴다든가 그런 건 없는지 좀 궁금합니다.
I have not heard anything about that. Mark, have you heard anything about that?
No.
The difficulty with using threads in Unity is that you cannot manipulate Unity objects, you cannot manipulate the scene, and you cannot call any Unity engine APIs. So generally, when we talk about using threading, it's useful for deserializing your own custom data types. It's also useful if you have a simulation that is not coupled to your scene. So if you keep your data in pure C# objects and tick it once per frame, perhaps, or run its logic on a thread, that's where we see threading being useful. Does that answer your question? Thank you. Anyone else? More questions? Just raise a hand. We have one here.
오픈GLES 2.0에서는 ETC2 텍스처 포맷을 지원을 안 해주는 걸로 알고 있는데요. 이제 안드로이드 2.3 같은 저사양 단말기를 주로 이제 지원을 해준다고 하면은 ETC2를 그래도 사용을 하는 게 좋은지, 아니면은 기존의 ETC1 포맷을 계속 사용을 하는 게 좋은지 여쭤보고 싶습니다.
There's no one format you can use for every device on low-end Android. You have to use the specific texture compression that each of the different GPU vendors supports. So You can use ETC1 if you don't have alpha in your image. Beyond that, you need to look at using like ASTC or, say, for example, DXT on NVIDIA Tegra chipsets. It's very specific to the GPU manufacturer. Now, in about the last 3 years, you have OpenGLS 3, so you can use ETC2 on all devices, which is good. And maybe around the last year, you can use ASTC on all new devices. And ASTC also works on iOS, so you can use the same texture compressions for both platforms. Does that answer your question?
More questions? Over here, over here. Let's go with this one first, and you've been waiting, I'm sorry. You'll be next.
안녕하세요. iOS랑 안드로이드 관련해서는 들었는데 그 리눅스 플랫폼에서의 그 리소스 최적화, 그러니까 압축 포맷이나 아니면 예를 들면 지금 오디오나 영상 같은 거를 지금 AVI나 이런 MP4를 쓰는 게 아니라 OGG나 OGV를 썼을 때 성능이 더 좋은지랑 그다음에 이미지를 압축할 때 기본적으로 레코멘드하는 게 있는지 리눅스 우분투 플랫폼에서 사용할 때 최적화 방법에 대한 팁을 듣고 싶습니다.
I've never actually dealt with an application that is running on Linux, but I imagine, okay, so talking about compression, compression is generally always good. It reduces the memory bandwidth it takes to upload your texture to the device, and it to the GPU, and generally saves GPU memory. I believe since Linux, I'm assuming, are you talking about Linux standalone, Linux PCs? Yes? No?
네, 맞습니다.
Yes. Okay. Since, for Linux on PC, you have to deal with the general problem of hardware fragmentation. So you have many different kinds of GPU devices to deal with. Same problem as Android. You essentially have to detect which kind of GPU your customer is using and upload a texture format that is supported by its GPU. For other optimization tips, the best thing you can probably do is, unfortunately, grab a Windows machine and try running VTune on it, or grab a Mac and try running instruments on OS X.
There are supported versions of the Intel VTune and Intel graphics performance analyzers for Linux. So you could use those tools, much in the way that you use the instruments. They give very good call tree information for time, and their GPU tools are very good. And I think AMD has good GPU performance tools for Linux. I don't know about NVIDIA, I've never actually looked for those, but it's similar to the Android, where you have to look at the GPU manufacturers and what they actually support.
Thank you. We had one more question over here.
일단 제이슨 같은 텍스트 포맷 대신에 아까 스크립터블 오브젝트를 사용하라고 하셨는데, 제가 테스트를 해본 결과 스크립터블 오브젝트 같은 경우에 같은 데이터 구조라 하더라도 파일 사이즈에 있어서 되게 큰 경향을 보이더라고요. 그래서 그렇게 파일 사이즈가 큰 경우에도 오히려 이게 로드 타임에는 이런 바이너리 포맷을 사용하는 게 더 이득인지 그 부분이 알고 싶습니다.
It depends on the details of your JSON parser. So if you are getting only certain values out of that large JSON file, then yes, only parsing a few pieces of text will be faster than parsing an enormous file that is binary, because Unity does have to deserialize and load the entire scriptable object. So in that case, yes, it would be better to use a format, a text format. Or, if possible, since you are only loading certain pieces of the data, it may be better in that case to split the data up, as I mentioned earlier. If you can predict which pieces of data you're going to need, and only load the individual binary scriptable objects for those pieces of data, that may improve performance even further. Again, don't optimize if you don't need it. Other questions? Oh, one more.
아까 5.3에 JSON Utility라는 클래스를 제공한다고 하셨는데 이게 다른 JSON 라이브러리하고 비교한 그런 데이터가 혹시 있으신지?
There are a lot of JSON libraries out there. Do you have any numbers off the top of your head?
I don't have any hard figures that I could display or quote, but we did run some tests on various JSON libraries when we were purposely trying to make something slow. And was it the Newtonsoft was like crazy slow. And then we used
10 times slower.
Yeah, it was like 10 times slower, and then we used tried lit JSON, and then it was extremely fast. So I don't have any numbers that I can quote to give you suggestions on what to use, but it's one of those things, construct a simple test and just try them all to see which one's faster.
Other questions? Just raise your hand if you have a question. Oh, we have one more? Yeah, please.
저희는 유니티 프로파일러를 많이 쓰는데요. 거기 보다 보면 그 오버헤드 항목이 있어요. 근데 그 오버헤드에 대해서 유니티 매뉴얼상에 그게 어떤 걸로 구성되어 있는지가 없어서 저희가 그 부분을 어떤 걸 자꾸 최적화를 해야 될지 고민할 때가 많거든요. 그 부분에 대해서 좀 설명을 해주실 수 있는지.
Yeah. Okay.
Do you want to take this?
Yeah, I can. So overhead is actually any time that the Unity profiler does not have. In the Unity source code, the reason we can actually break down many of those items into the Unity profiler is that we have instrumentation inside the source code that says this block of code becomes this thing in the profiler. Overhead is all CPU time that falls outside of one of those blocks. So unfortunately, it could be anything inside the Unity engine without instrumentation. In that case, if you're on some kind of platform where you have access to IL to CPP, try using a native code profiler. Try using vTune or Instruments or one of the other tools that we've mentioned, because those can actually dig into the things marked overhead. They have complete method level resolution, as we showed you during the talk. I wish I could offer you more than that.
It sometimes includes things like vsync, especially on platforms where the Unity profiler isn't providing GPU profiling information. It can sometimes include things that are happening there as we're sending commands to the GPU and like waiting on the frame to finish. So sometimes overhead can actually be your GPU time for your frame. So that's worth bearing in mind, but there's no set rules for which devices this happens on and which ones it doesn't. This is why we recommend the native platform tools for really, really optimizing things.
More questions? Hands? Okay, I guess thank you very much. If you see us around the conference, feel free to ask us any questions that you think of.